Good morning, everybody. This class is dedicated to computation of convex hull. At first, definition. What is the convex hull of a shape in general? In general, the convex hull of a shape is the smallest convex shape that encloses the initial shape. Very general definition. In our case, we are only going to deal with sets of points in the plane. Okay, we have a set of point S that contains n points. So, how could we construct that smallest convex area that encloses this set of points? We can imagine the following construction. Imagine a spring, okay, in tension, that we put around my set of points. Imagine that every point is like a needle, okay? And we are going to release the spring. So the spring is going to contract, and at some point is stopped by a certain number of the points, which in fact those points that touches the spring when it contracts like that are the points of the convex hull of the set of points. First, we see that the convex hull of S is a subset of S. So convex hull of S is a subset, okay, of S. It's a set of points, subset of those points. And we assume that the number of points of the convex hull of S is equal to H, okay, which is less or equal to N. Then, in order to store CH of S, we're going to assume that the points are going to be stored in the clockwise direction, like that. So if you have to do a computation in a program that computes convex hull, the result will be a list of points in clockwise order. Okay, so that you can draw them with both, for example, easily one by one. So, how could we compute now the convex hull? Imagine an algorithm that would compute that quite efficiently. We are going to go through three algorithms that compute convex hull so that you can have the choice if you want to choose this subject for your project. The first one is maybe a little bit naive, but not stupid. Okay? And so the first thing that you have to look to build an algorithm is there any geometrical property that I can use to build the convex hull? So let's imagine that we have P1 and P2. We have a segment that goes from P1 to P2, and it's supposed to be in the clockwise direction. So what is very important to look at? If I look at P1 to 2 as a reference line, all other points of the set are going to be on the right of the reference line P1, P2. What does it mean on the right? Imagine that you are walking on this line and you look at all the other points, they are all on your right. It has, of course, a mathematical signification. If I take, okay, this as a reference, and if I measure an angle theta here between the reference line P1, P2 and another point, okay, P2 as reference, then the angle will be negative. Okay, always negative. It cannot be positive. Another way we'll see in the second algorithm is to talk about areas of triangles. It's more efficient, but let's start with that definition. So with this simple remark, we are going to devise a first algorithm which is called Jarvis March. I am going to describe the algorithm and then compute its complexity. When I talked about intersection of line on the previous podcast, I gave you a complete algorithm in C that was able to compute those intersections. In this case, I'm not going to give you the algorithm because this could be part of your project, so I don't want to do that. But I'm going to try to be as clear as possible on data structure that could be used and also on the algorithm itself. First, Jarvis March. Imagine a simple set of those 5 points. Okay, I'll say P1, P2, P3, P4, and P5. First, a remark. Imagine we use the simple system of coordinates, Euclidean system of coordinates. There are some specific points that are easy to find that eventually belongs to the convex hull. One point, and I'll explain that obviously belongs to the convex point is the lowest point. The point which has the lowest y coordinate. Okay, this point eventually belongs to the convex hull because if I take as a reference this first reference line, okay, all the points are above it. So it means that if P1 was not belonging to the convex hull, there would exist another point here, okay, that would, let's say, be here, and that would be such that P1 is on the right of this oriented edge. But this is, of course, impossible. So all the other ones, all the other possible pairs of points generate a line which is such that P1 is on the right of it. So it's impossible. The situation like that is impossible. So the lowest point is clearly belonging to the convex hull. So we can start with this point. Okay, we start with this point. This is easy. Let's start with P1. And let's now look at angles. Okay? And let's look at the point that forms the minimum angle with respect to the reference, the first reference line. Okay? This point belongs to the convex hull. Okay, because if you look at this line, okay, in this direction, like that, all other points are on the right of this line. This is the definition of the convex hull. Great. P2 belongs then to the convex hull. Let's now draw a new reference line. This is my ref for the second point. And let's compute the point here that has the minimum angle. Again, so point P4 belongs to the convex hull. And you have now a new reference. And then this process eventually leads to the computation of the convex hull, computing each time a new reference and browsing in a brute force on all the points to get the next one. So what is the complexity of Jarvis March? First, what is the number of iterations that we do? In fact, we only iterate once per point of the convex hull. So the first loop is of size h. We are going to go one by one to every point of the convex hull. Great. And so at each of the iteration, we do the brute force stuff. We go through all the points. So it's h multiplied by x. So the complexity is h multiplied by n. Is it bad? Is it good? Depends. So it could be very good if we have a situation where we have the smallest possible convex hull of a set of points, which is a triangle, and all the other points are inside. The convex hull will be there, so the complexity here will be of the order of 3 multiplied by n, which is superb. But it could be very bad. It could be very bad in the sense that if we have, let's say, a situation where every point is on the convex hull, we will have an algorithm which is of the order of n squared. So I'm going to stop here, but before stopping, you should think about first what happens if we have 3 points that are aligned. I'm going to deal with that. And second thing, could we do better? Could we make Jarvis march better in such a way that it's not going to be sometimes good, sometimes bad, but that evolving Jarvis march in such a way that it's always going to be good, the best solution would be essentially n log n. I'm stopping now. The second video is coming.